Let's review confidence intervals when population standard deviation is not known. In your classroom, you took a poll of students in your class. Answer each of the following questions about confidence intervals. 5 students were polled with a mean age of 27. Your sample's standard deviation is 6. Construct a confidence interval with 90% confidence. So let's talk a little bit about what we're trying to do here. We want to know the information about our population. We want to know our classroom's average age, or our mean age. So what we do is we take a sample to try to infer or tell us what that could be. Now, of course, this is a good start on determining our classroom age, but it will never be completely accurate unless we take every single person in our classroom and poll them and find out their age. So what we're doing now is using a sample to try to give us information about the population. Now, obviously, in this example, you could easily poll the rest of the classroom, but often you don't have the luxury of polling everybody in a population. For instance, if you wanted to know something about Canadians, there's over 35 million people you'd have to poll. It's a lot easier just to use a confidence interval and sample a certain section of the population. A confidence interval will give us a range that will tell us with a 90% confidence where the true population mean or average will fall into. So we'll go ahead and show that here with this example. So if 5 students were polled with a mean age of 27, your sample standard deviation is 6. Construct a confidence interval with 90% confidence. To start, we need to determine our degrees of freedom. So we're going to be using what's called a t-table. And when we use our t-table, we need to start with a degree of freedom. So the degree of freedom in this regard, and you should always look this up, because degree of freedom can change. The formula will change for it, depending on the usage. But for a t-table, our degree of freedom is n minus 1, and that will determine our degrees of freedom. So our degree of freedom would be 5 minus 1, or 4. We are then going to set up our range using the following formula. Again, this is a range, so we have a plus minus based on our observation. Now don't be overwhelmed by this formula. There does look to be a lot of variables, but really this is all subscript, and you can just make this one number. So what we're looking for is a t distribution. We need to find our t, which we'll find in our t-table, or our probability from our t-table. So first we need to determine, is this a one-tail or two-tail probability? So the way we can determine that is if it is going to we wanted to know if the range would be less or higher or lower than 27. So based on that, if we have a look at our standard distribution, we see that we could have numbers that are above our average and below. So we have two-table. If it was asking if it was higher than, so is the average age higher than 27? Well, then we wouldn't need to consider being lower than, because we're only considering one. So this would be a one-tail. So in this case, we have a two-tail probability. So we can review our t-table. We understand that our degree of freedom is 4. We have a two-tail situation here, and we have a 90% confidence. Looking at our t-table, we can go ahead and, with 90% confidence, that would be this area right here, 0.10. The reason is 90% would be on the, we could have 5% on one tail and 5% on the other table. We have a degree of freedom of 4, so we can find here 2.132. Let's enter that into our formula. So our average of our sample is 27. It's our observation. Plus minus 2.132 multiplied by our standard deviation of our sample, which is 6, divided by the square root of our sample size, which is 5. We get a final answer of 27 plus minus 5.72. So this gives us a range of 27 less 5.72, which is 21.28, all the way to 27 plus 5.72 of 32.72. So, in layman's terms, what this means is that based on our 5 students polled, our sample of 5, with the mean age of 27, our sample standard deviation, and a 90% confidence. Now remember, this means that if you were to run this poll with 5 different students 10 times, you can expect to be wrong 1 time. But this will be right 9 out of 10 times. Is our population mean will fall between this range. So let's try the same thing but with 95% confidence. So our degrees of freedom remain the same. So let's have a look at our table. So now we have 95% confidence. Now again, this is still a two-tail. And we see it for each tail, so one table would be about 2.5%, and the total would be 5%. That's our significance, so our confidence level is higher now. And so you can make a guess on what's going to happen if we have a higher confidence. So if we were to run this sample again with 5 students, but now, if we were to do it 20 times, we need to be right 19 times. In the last example, if we were to do it 20 times, we only had to be right 18 times. So let's see what happens. Here we can find our T amount, degree of freedom 4, and 5%. We get 2.776. And we get our mean of 27 plus minus 7.45. So let's have a look at our range. Our range is 19.55 So, with 95% confidence, we have a larger range. So this tells us, based on our sample information, our actual population mean will fall with a 95% confidence within this range. Now, as you can see, this is a larger range than with 90% confidence. And this makes sense because at 95% confidence, we are not allowing ourselves to be wrong as much. We are saying that in 20 samples, random samples, we have to be correct on this 19 out of 20 times. In this scenario, we're saying in 20 samples, if we're to do this poll 20 different times with 20 different students, we only have to be right 18 times. So if we can allow ourselves to be wrong more, we're going to have a smaller sample. If we are saying that we absolutely need the correct answer, and up to we can only allow ourselves to be wrong less, 1 in 20 times, we're going to receive a larger range. So let's have a look and see what happens when we increase our sample to 30 students. All the other information remains the same. We're going to use a 90% confidence. So our degrees of freedom is now 30 minus 1, or 29. We still have a two-tail situation. So let's have a look at our t-table. Here we can see we have our degree of freedom at 29. And we can go to our, now we're at 90% confidence again. So we have our 10% significance. And we get 1.699. So a mean of 27 plus minus 1.699, a sample standard deviation of 6, and a sample size of 30. What we get is a mean of 27 plus minus 1.86. Our range is now 25.14 to 28.86. So we have the same confidence level as we did originally, but the difference is that we now have a different sample size. So before, when we had a sample size of only 5 students, we had a much larger range. Again, this makes sense if you think about it. The more students we sample, the higher likelihood it is that we get the true population mean. So that means with a 90% confidence, based on our larger sample, we can expect our population mean to fall within here. And if you think of it on a grander scale, if you wanted to know information about Canadians, well, the closer you get to sampling all 35 million Canadians, the more likely you are to have the exact mean. If you were to sample 10 Canadians, you would have an extremely wide range. If you were to sample 10 million Canadians, you would probably have a very narrow range. So you can decrease the size of your range by allowing yourself allowing yourself to have more error with a lower confidence level, or you can decrease the size of your range by having higher samples. And that is how we use confidence intervals to determine what our population mean is, and using the different confidence rates to determine where we are comfortable with that information.